Okay, so at the end of the video, we were writing the electrons out for sodium. We had done it out longhand in the video before, but now that we have our rules, we can write it like this. There are 2 in the n equals 1, L equals 0, so we write it as 1s2. There are 2 in the n equals 2, L equals 0, so we write it as 2s2. When we get to L equals 1, n equals 2, L equals 1, there's 1, 2, 3, 4, 5, and then I went off the page. There's the 6th one. So it's n equals 2, L equals 1, so it's a p. And there's 6 of them, so 2p, 6. And then the last one went into the n equals 3, L equals 0, so that would be 3 back to s. So 3s1. And so this is a much more concise way of writing it than all of this, but it shows exactly the same thing. That's aluminum, that's sodium. If we wanted to do the next one in the periodic table, Z equals 12, magnesium, then all we have to do is just add one more here, and it would become 1s2, 2s2, 2p6, 3s2. And so this is called the electron configuration. And I highly recommend it over this stuff. Electron configuration. But it comes from everything that Heisenberg and Born and Sommerfeld and Pauli and Dirac and Hund and all of them did together. Okay, so you figure out how many electrons in the atom, and then you start at the lowest energy and you assign the electrons. Now, if in an ideal world, we would go in order. We would go 1s and then 2s, 2p, and then 3s, 3p, 3d, etc. But what we've learned through time is that they don't always fill in order. And so we use something that is called off-bows diagram. And so to make off-bows diagram, you line up your 1s, 2s, 3s, 4s, 5s, 6s, 7x, all s under each other. And then do the same with the p's, 2p, 3p, 4p, 5p, 6p, 7p, and then 3d, 4d, 5d, 6d, 7d, and then with the SPDF is 4f, 5f, 6f. I know we're not there yet. 7f, and I mean you could keep going, right, forever if you want it. It's gonna bother me if I get this 9s. Okay, and we would just keep going out. This one would be the 5G, and then a 6G. Okay, so you line it up like this, and then what did I do with my colored pen? And then you go down this way, so they fill on the diagonal. So everything goes in order until you get to 3p. And instead of then going to 3d, it goes to 4s. Why? Because they'll always fill so that... I drew them a little too close together. They always fill so that the most stable ones fill first. Most stable, lowest energy. And so the 4s is going to fill before the 3d. One of the reasons they think is because it's easier to add and subtract from the 4s than it is the 3d. I think it's also because it's easier to fill the 4s. You only need 2 to fill the 4s, and it's more stable when it's full. You need 10 for the 3d, and so it's not as stable. When it's not full, it's not as stable. So it would go 1s2, 2s2, 2... P6, 3s2, 3p6, and then it would go to 4s2. Okay, we don't, and then 3d10. So you use Aufbau's diagram to fill them, and I would highly suggest that whenever you go to do these, write this down on the side of your page and follow it, okay? There used to be some chemists that would then make their students rearrange these, but that defeats the purpose. Doing it like this shows you exactly which ones have more energy and which ones don't, but we'll come back and talk about that tomorrow. There's just one more thing, and that is these can get kind of long and arduous when you're doing big guys. I mean, not as long as writing them all out in that chart, but still pretty long. So when we look at the periodic table, the noble gases over here have a full outer shell. And so there's another method. It's still an electron configuration, but it's kind of like a shortcut of the electron configuration. And it's something that's called the Kernel Method. And really, if we were in class, you would only be allowed to use this when I specifically asked you. So it's called the Kernel Method. Sometimes it's called the core method. And so let's suppose I'm going to pick something that's rather large. Maybe I won't go too big. I'll pick potassium. It's 19. Okay, so K set equals 19. So you do 1s2, 2s2, 2p6, and then you double check and you say, oh, that's 10. I still have, remember I'm using this, I still have 9 more to go. So 3s2, 3p6, now I'm at 18, so then I have one more, 4s1. That's potassium. But if I didn't want to write all of this out, I could use the Kernel Method. Now, and like I said, when you're starting, I want you to write them all out until you get used to it. But the Kernel Method is, you go to the noble gas that precedes it. So what's the noble gas that's before potassium, which is potassium's 19? It would be argon, which is 18. And so you would write like a square bracket, AR, close the bracket, so that means like it's everything, the electron configuration for argon, and then you would write 4s1. And this is the Kernel Method for potassium, whereas this is the full written out one, okay? So as you do some examples of these tonight, I want you to only use the Kernel Method when they ask. The other ones you use the long ones. Tomorrow we'll talk about how they're connected with the periodic table, but I don't want to ruin that on you because I want you to write some of these out. And then tomorrow we'll talk about the fact that even with Aufbau's diagram, there are some exceptions. And the exceptions have to do with it's always more stable if there's a full outer shell. But I don't want to ruin the end of the story. You need to wait for that one. Okay? So this evening, if I could find the right page, this page, I would like you to do questions 4 to 9 on the back. Okay? And it's just writing out the electron configurations. So it's a PDF that I'll post. Okay.